Welcome to Advent of Code in F-star. I'm a little late getting started, so a new puzzle's going to go up any second now. So if you haven't seen F-star before, it's a dependently typed functional programming language, which means you can prove things about your program using types. Okay, so we got a numeric grid, kind of like yesterday. It's only 10 by 10. Okay. During a single step, we increase the energy level of each octopus by 1. Any octopus with energy level greater than 9 flashes. So 10 or more. This increases the energy level of all adjacent octopuses by 1, including octopuses that are diagonally adjacent. If this causes an octopus to have an energy level greater than 9, it also flashes. An octopus can only flash at most once per step. Okay. Any octopus that's flashed has its energy level set to 0. Okay. So we got a sort of cellular automata today. Okay. So we're asked to simulate 100 steps and count the number of flashes. And I bet we're going to be asked to do more flashes in part 2. So, let's see what we can do about this. What's our puzzle input look like? All right, let's copy yesterday's, no, day 9's definitions. I don't know if we're going to need the neighbor function. So what's going to be tricky here? You're adding one, it's not hard. It seems very hard to do this in a functional manner. It's not impossible, but I'm wondering if I should switch to an imperative model. So we could do that by filling this matrix up with references. We'd still have to solve the problem of how do we figure out efficiently how to update our neighbors. We'd prefer not to scan the array each time. Do we need... Let's think about this. Yeah, I think I'm going to use the idea of a matrix of references, and we'll see whether we can whether we should all right, so we do need this neighborhood. I guess one thing I'm wondering about is, does the order matter? What can we prove that it does or does not to handle the flashes? I think it should not. As long as we don't. Yeah, this guy has to be at 0 at the end of the step, no matter how many flashes. So we can't just set him to 0 and update everybody else. We have to set him to 0, mark that he's flashed this round, and not increase him. Okay, I think it still makes sense to do it in an imperative fashion, so I'm going to pull in F star's state effect, which lets us do stateful computation. And so, all right, let's fix this back to, all right, so we got a function, right, this is a function that gives us the neighborhood of a particular point. And this is still defined for, yes, the previous problem where it's only orthogonal, so let's fix this. So, okay, there's one row, and the middle row, and bottom row. Okay, all good so far. So let's define a type to hold our octopodes. So I don't think we want to just use a... All right, so one option is we just do that. But I think we need to... Okay, but if we're going to update them, it needs to be a reference to that. And what I'd like us to do is actually go a step further and define two octopus states. An octopus can either have flashed this round or be normal and have a number attached to it. Octopus. What am I doing wrong here? Spelling. Today's going to be challenging for spelling. Okay, so we want a reference to our octopus type. Why is that giving me so much trouble? All right. So this is ref basically means pointer. So let's write some IO functions. So we can take the day 9 solution again. All right, there's our parse row. And we can just fix the expected length. Okay, I guess we can't. Because I recursed. All right. All right, this is going to return a vector of octopus, though. Why? Okay. All right, so parse the rest of the row. Okay, and the string S. Okay. So these are all going to be normal octopuses, octopi. Okay, so this is just a big match statement. I'll fill in the numbers in a minute. Okay, but this isn't the right type. All right, so our matrix is going to be our pointers, so we need to return references to Octopus. And this can no longer be a total function, it has to be have effect st. All right, so that is how we allocate a new pointer in the st effect. I just call alloc. All right, so let me. If we had not been lazy and I had written the ASCII code manipulation, then this would all just be one line. But I was lazy on the previous day, and I'm still lazy today. Oop, all those are in the wrong place. Oh, no, it's. Let me look up last time I used this. So it was. It was the. Oh no, I used it in a warm up for last year. I used it for a boat problem. No, I used it this year. D2. Okay. Oh, okay. That's the one where it has a condition. So with let me make that bigger. There are two forms of the effect. So an effect's a model of computation. So big S little t is without any preconditions or postconditions, and capital S capital T is with preconditions and postconditions. All right, so are we okay there now? So we can use a total in function. Okay, this needs to be a ref octopus. No, this was right. This needed to be, this is our input. this was wrong. Okay, there we go. Expect all the rows to be length 10. And we need to specify the effect. The default effect is total. All right, we're just using our recursive function above to walk through characters one at a time, figure out what the octopus's energy value is. We're good. All right. So ML is a superset of the ST effect. So we should be able to use this. Okay, so this is going to be a don't need the width. Okay, good. All right, now we need the parse matrix function itself. Except it's going to be simpler because our width is fixed and our height is fixed. So we can just return that. We don't have to do any of this actually. But we do have to check its size. So if length M is not 10, then we fail. Else, we should just be able to return M. It's a list that has the right length. Yep. Okay, so we defined this to be a list of a vector of vectors, each have length 10. We checked that it must have length 10, and then we can apply that. We can return it and it has the right type. Okay. So there's our input. Let's write our print function, just in case we need to debug this, which seems likely. Better yet, let us copy over our pile of code that all right, so what all this is it's just a function to create a list of natural numbers between start and end, and prove that it has the right length. And this is unnecessarily complicated, I think, but it's the only way I could get it to work when I was doing warm-up. So let's feed all that into the proof state. Feed it to the star interpreter and type check it. So basically, this is the only thing we need. Is it's a range between start, which we're just going to use 0, and end, which we're just going to use 9, and it guarantees that everything everything in the list is between that, and this lemma tells us that it has the length we would expect. All right. So we can use that to iterate over our x and y coordinates. So, but which is a little simpler because we're gonna make this our print statement. So it just returns a unit. Unit is it's not a void type because there is a unit object. It's written open parentheses, close parentheses, but you're not allowed to take no arguments or return a value. But you can use you can use unit, and there's only one unit. So it's sort of like using void in C++ or the none. Maybe it's closer to the none type in Python, except it doesn't have the semantics of it's a special value. Okay, map. Since we've got a fixed length, we don't actually need all that. Let me actually pull that back out, and we'll do it a simpler way. So, okay, we're going to call this 0 to 9, and it's okay. So it's going to be a list of natural numbers, and each natural number is going to be less than or equal to 9. And the list is going to have, so we need a variable name for the list. The list is going to have length 10. So we'll use the literal list. And we're going to ask the normalizer, which is sort of F-star's execution engine. It knows how to do variable substitution and expand functions, and it's got a whole list of things it can do. So it's not what actually executes our code, because we're going to translate to OCaml, but it's how F-star knows how to expand things in order to prove properties of the program. Okay, so assert norm length lit equals 10. Lit. Okay. There we go. All right. Good. Do we need that? I'll keep it around just in case we do. Why did I need to do this? Let's give this a try. All right, so the function this is going to match we're gonna grab the octopus. Okay, but that is actually a reference to an octopus, so we need to unreference it. And the shorthand for that, oops, is bang. So if it's, what should we call our constructors? Then we're going to print a dot, and if it's normal, then we're going to print I don't think I loaded that. I really need to have a print int function to keep doing this all the time. All right. Oops. All right, so there's our function. And since we specified we got a unit backer and a list of units, we need to patch that up. Actually, we need to do more. We need to print a new line. Can be our value All right. So it thinks this function is a total function. All right, let's rewrite it. All right, so there's our y value, and in that context, we want to take an x value. Okay, in oh, okay, that's the problem. Probably got the type right, but okay. So the problem is the semicolon operator can only take a unit type on its left. And it says, hey, you gave me a list of units. Does list have... iter? Yes, so that's the function we should be using. What does iter I do? Oh. Well, dang. That's what we should have been doing. All right, I'll remember that. That's there. Before I was trying to use the total type. I don't know if it's there, but it should be. Okay. So let's try taking in our input and printing it back out. Make sure everything's working okay. Go back to and print. All right. So what's the example input? There's that. And where's our real input? All right. Oops. Copying the make file. The make file, it's not much in there. It just calls fstar to generate OCaml code and runs the OCaml. So a lot of it is set up in this included make file that comes with fstar. All right. Looks pretty good. So let us all right. So we're going to write something similar to our print statement that's going to add 1 to everybody. So this will be pretty simple. We just say value at myx colon equals, and that's the shortcut for setting a value. Oh, okay. No, we can't do that because we used our type. So we're I just was wondering if we're going to want a version of this that works on a list of neighbors, and we might, but let's at least get this version right. So if it's flash, then we don't want to do anything. Otherwise, we want value at x. I want it to be normal with v plus 1. Okay. So we can try that out. Okay. I mean, it won't come out. I guess it will come out nice. Aren't there no 9s in the initial state? Okay. So the thing we could do is have this return a list of every octopus that is going to flash. And then we wouldn't have to go through the matrix again. I'm the only reason I'm worrying about this is that in part 2, it feels like we're going to ask to be going a larger number of iterations. But I'm not sure it will make a difference. Why don't we all right, I'm trying to think. We need to count the number of flashes. We can do that when we reset. So let's write that. Um, So do we have a fold left with the right state? We do. I'm actually I'm gonna change these to the more restrictive state. So the difference. Why does it think that have? Why does it think that has type ML? Oh, this version this has type. This has effect ML. Okay. Uh, that's unfortunate. All right. So the difference is ST is stateful computation. So we can set values on the heap like this one does. ML adds to that it can throw exceptions or do IO. Just IO, I think. You probably shouldn't listen to me. I haven't worked much with the intermediate effects. There's div for divergent computation and EXN for ones that show exception, and ML is basically everything. It's the most permissive model of computation. All right, so we gotta use ML if we're going to use fold left. So I'm gonna take a count and an integer and yeah, count and an integer, and if it's flash, then return count plus 1, otherwise return count. Oops. So the fold operation works as in other functional programming languages. Okay, we gave it integer rather than natural number. Natural numbers are just ints bounded to be greater than or equal to 0. There we go. All right. So while we're counting them, we should set them back to their normal value. So we're going to that is normal 0. Okay. So that's the second half. I've been avoiding the first half is Let us all right, I guess I'm thinking we should return a set of pairs. And then go and update those pairs. So might as well do this somewhat efficiently. I have no hope I'm going to be able to prove things about this process. All right. What is it complaining about? Oh. Okay. All right. Flashed. Shouldn't happen. I wish we could guarantee that was the case. I mean, we could put a type on M that said that was the case. And we could put it in the preconditions to the all type. Let's think about coming back and doing that later. All right. Okay, so if it's normal, we want to increase the value by 1. And if is it greater than 9? All right, I'm going to use a trick. I did earlier and use list collect. So that takes each function invocation gives us a list, and the result is appending all those lists together. So that's an easy way to take either 0 or 1 element from each function call. All right. So let's define one step. All right, so the first thing is add 1 to everything and return a list. So and then for all those flashed, we need to go back and bump their neighbors and mark them as flashed. And I think I convinced myself that we can do them in any order, and we don't have to do them all simultaneously. So if you're an octopus and you're sitting there, it doesn't matter the order in which your two neighbors flash. They're both going to drive you over 9 or not. You're going to end up at the same value. What matters is that if you do flash, you end up at 0 at the end of the step, which we guaranteed here. So it'd be awfully nice to have post conditions stating that after this exited, everybody was normal. It seems tricky to prove. Let's try proving it just for this step. Um, and I need to look up what the, okay, so all ML is all with the trivial conditions. So we want all with pre and post. Okay. Oh, okay. No, so these are functions from on the heap. Okay, so I'm just gonna check the syntax here. Is that still parse? Post. Okay, so the post condition is a function on the heap, the heap before the function, the return value, and the heap afterwards. Okay, so what we want to say is the octopus we edited is normal at the end of this function. So get the reference and how do we get stuff out of the heap? Select. We could say, hey, it modified only the one value. We can do that too, since we're at it. We really ought to put this in a separate function, but what I've been doing is putting it in here so we get both M and Y in scope rather than having to pass them in again. So let me go back. All right, so modifies only between H1 and when we look at the new heap at that location, it's only got a normal octopus. And it's taking, oh no, we got it confused. So we got to, all right. What is its problem? Oh, we didn't complete writing that function. All right, and then we need heap. All right, I'm not sure what that's about, but I think it's that the heap the F-star standard library reuses a lot of the same identifiers, and that can make it hard to use them in the same function. Okay, so it type checked. So it was able to prove that in both these cases, we end up with a normal octopus, whether we set it to be normal or whether it originally was normal. Okay, that's pretty good. So doing it so that everything in M is normal is hard, but we at least put a little check there. All right. So all right. So we're going to write a recursive function. So it's going to return, take our matrix and our list of this type of indices, of inbound indices. All right, and what we want to do is Okay, so our list might have some redundancies, I think is the easiest way to do it. Right, because we're going to process this list and we're going to add to it if we push some of our neighbors over, and some octopi are going to be the neighbors of more than one. So let's just check that we haven't flashed this one. Okay. All right, if the list is empty, then we're done. Otherwise, we're going to process the head. So we match on we can do better than that. We can pattern match down and deconstruct the pair. All right, so if it's flashed already, then we're just gonna pass in the tail. Right. Otherwise, if it's a normal and where its value really doesn't matter, it should be greater than 9, but I don't think we actually need to know what it is. So we're going to get its neighbors. Neighborhood. So that's a list of everybody we need to update. So let's first set that up. Okay, so we changed the state of the one that was on our list. And we need to increment the value of each of these. So let's split that out as a function. Okay, so okay, and just do our normal recursion again here. If the neighbor list is empty, then we're done. Otherwise, it's Y, X, and the rest of the list. So if it's already flashed, that's what I wanted to do. Okay, so this okay, so increments neighbors of a flashed octopus, and it returns any that are now. We can optimize here, I guess. Right, if they're already greater than 9, they're already going to flash. We don't have to add more values to them. Okay. And oh, all right. So that's what I was going to do. Is I was going to define this as a interior function. So so f of I should have defined a type for this. Let's do that. All right. Didn't I put this comment in already? I guess not. Okay. Place. This returns list chord and it's an ML function. Okay. Y is first, then second, All right. Okay, good. So what we want to do is let the new flashed is we could do all that in one line, but that's okay. All right. So we have updated everybody in the neighborhood. We have potentially a new list of octopi that go on the end of our list. So we just want to recursively call back in with uh, tail and the new flashed at the end. I think we should be able to do that in either order. Okay, I didn't write this function right. It's expecting natural numbers and it needs to be ref octopus. Yeah, we can put all that up above. Okay. Okay. The right thing would be have an extra implicit parameter here. F star implicit parameters start with the pound sign, put the hash sign, and we could take the type of a matrix as a third argument. But right, let's see if that makes it happier. Okay. Um, okay, I wrote this to return the values rather than the coordinates. Okay. I'm just trying to think. Could we or should we make it work that way? I'm unhappy passing the list of pointers around. It seems more error prone. So let's specialize this. All right, it's still type checked. We don't want references to coordinates. We just want the coordinates. All right, kind of sloppy, but all right. Reset. Okay. So let's do a couple steps on the example. I really wish it would just let us ignore the value. There we go. That ignores the value. All right, so we'll do 2 iterations. Oop, oop. Oh, that's no messing up. All right, messing up my windows inside the VM. It looks pretty good. Yeah, I think we're in good shape. All right, so now we just gotta do it for um. Now we just have to do it for how many iterations? 100 steps. And sum them all up. All right. Um, all right. So let um, I want to be careful here because we are modifying this state. So we need to be sure. Okay, Yeah, so let's step first, and then, all right, if n equals 0, then 0 else. And this is not properly tail recursive, which we might need to fix for part 2. So let's just do it right. Steps m, n minus 1, and toad plus flashed. All right, so there's our loop. We call it one time. If we call it with 1, n equals 1, we do one step and then return the value. So we don't have an off by 1 error. We're not going to do it 99 times. All right. All right, let's try that out. That is nowhere close to correct. Our matrix is correct. So that's good. Let us I'm counting backwards, but that's fine. Yeah, those numbers are just not right. Okay, so that probably means we're only counting, doing something silly like only counting one row. So given the count, oh, all right, I see it. Um, me rename these so it is clear. And we want to start with the column count instead of at 0. There we go. That looks right. Okay. I had been thinking for verifying the correctness of these matrix functions, it would be nice if we had a matrix to list function, and then we could make a property like, then we could use the built-in count function. But we could also, it would be easier to prove things about it, because right now if we want to prove things, we have to sort of iterate twice, and that gets gross. But it means we're not really using everything in F star to our advantage. Anyway, let's see if we solve part 1. We're not too horribly slow. Okay, let's create an answer. All right. So what is the first step during which all octopuses flash? All right. So we can do that. I think we can just do this. I better copy. Just in case. All right, so we know we already counted how many flashed on each step. So we don't need this. No, we need a counter. All right. So if if all of them flashed, then return the number of steps it took. And that's, let's start at 0. So that'll be steps plus 1. Otherwise, we do steps until sync, same matrix, steps plus 1. All right. Let's change the module name. Let's give that a try. don't have the... Well, that wasn't so bad. Let's check our answer to the example. So that was step 195. Yes. I was worried this was going to be, we're going to have to iterate thousands of iterations. All right. So, about 90 some minutes, not too bad. Yeah, about where we've been doing. So I'd really like to be able to prove more about the operation of our functions. Particularly this function where we had the bug. Could we prove that it does what we say it does? I'm not even sure we can prove something about functions with an ML effect. We should be able to, though. Well, what would it look like? Count is correct. So the first problem is only the values we're working with are all in the heap. So we need access to the heap. Which I'm not sure we can do. So let me check the tutorial and see if there are any hints. What this does is just puts them intrinsically these are all proofs about total functions. This is about how to avoid lots of anti-aliasing, which might be a big problem. To prove anything about the contents of the heap, we'd have to prove that none of the pointers are to the same octopus object. So we'd have to have 100 juice to inequalities of this sort. Um, hmm. I'm not seeing a way we can. I'm not seeing a way we can use a lemma. I think we could use a lemma if it took the heap, but we don't actually have access to the heap directly, and I don't think we could provide one. All right, what does this look like? No, these are all about total functions again. So a lemma is itself a function of the type ghost total with effect ghost total. So I think I don't think that's going to work. I think anything we wanted to prove about this function would have to be part of its post conditions, just like we did for the little function in the middle. And I don't think we'd be able to show. Let's give that a try. So what we want to say is we don't have. All right. So for all x member, if x is a member of 0 to 9, then right. So that's what we'd like to say about map row is it set everything in that row. My labels are backwards, I noticed, between column and row count. Well, we'd like to say that everything there has been reset. And like I said, I don't think we're going to be able to prove something about the sum. I don't think we're going to get that for free. Yeah, it can't prove that post condition all by itself. So I don't know. Uh, I know how to do things in lemmas where we can sort of break it down into smaller units and assert and see what it knows and what it doesn't know. This is trickier because it seems like something we could prove by induction, but we're not in a lemma, so we can't do induction. Um, so what that would look like is we'd need a stronger condition here. We'd need to say, let's try, let's try that a second. So we could do the induction in our map O functions pre. Wow. Okay, yes, it's the same thing. All right, so what I think we can do is we can require that the property we care about is true for all I need another variable name. So for all values of x, okay, so what we're saying is in the previous loop, we already ensured this property for everything less than x. And so now we're going to prove it for everything including x. Okay, that needs to be a. I'm going to call this x naught instead. All right, so that's I think what would be convincing. That looks like a loop invariant, sort of, right? We say before the heap had everything up to x, up to but not including an x, and after we run that, it's everything. All right. And I think we may need to parenthesize. Yeah, we need to parenthesize that. Huh. Subtyping check. Expected nat 10 nat. Well, it should be able to tell that. Let me copy that. Okay, it might not be able to take our. Oh, it took took our function before. It was all typed before. I think it's more likely that it can't prove that the precondition holds. Let me just double check that. Yeah, it's the same error, just with. I don't think it's the difference between the ML and the all effects. It should be that. Yeah. All right. I think we could maybe make this work. Let's cut things out until it works. It might be that we just can't use full left to do this sort of reasoning. Or it might be that we screwed up writing. Yeah. All right. So what if we let's put this back. All right. So it's happy with that. I can't tell whether it's the pre-requirement that's giving it grief, because that might not be modifiable to the. It should be fine. I don't understand the effect logic completely. So a different they form a partially ordered set. So some forms of computation can be converted to others, and it should work for everything, no matter what the precondition is. So I'm wondering if it's just having trouble telling us that the precondition check is failing. So why don't we try that? Let's just create an impossible to satisfy precondition and see if the error is the same. Yeah. So the problem is it's it's telling us there's a type error, but it's not giving us all the information about what's failing. I wonder if running with query stats will actually do any good. Kind of doubt it, but yeah, it's not being very precise. Let's try. Let's try moving this out to its own function. So let's make this. Okay. Okay. Oh, we need our matrix and our y value. All right. So it can prove our uh we can prove our condition. That's good. So it agrees that that is what the function does. So let's try to do the whole row. So we don't have any requirements. Oh, there it is. So we need to query this function with Octopus my. Which means we need to put column count somewhere else. So is the problem that we didn't specify that this was a natural number? No. Um, all right. So let's, all right. So either x equals 0 or okay, still happy. All right, so that wasn't the problem. What if we called this one at a time? What if we unrolled the loop? All right, we'll just return 0 or 1. All right, and we'll just do 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I don't know what's going on here. Be nice to figure it out. I was hoping it would tell me that it was. Okay, well, that's interesting. So it seems like it's. The error message is not specific enough. It's just unknown assertion failed. I can't tell if that's telling me that the post condition can't be proven or if the precondition to reset Octopus can't be proven. It seemed like the problem before. So I'm gonna check this in as is, but I'm gonna put a big expect failure mark there. Because I think we've given it everything we need to prove, but all right, and we can clean this up. Oh, except we. Why is this failing now? Oh, we still have the false in there. All right. There we go. All right. Well, I'm going to call it a night. I'll check this in with a note. It's too bad that we can't prove that at least that it resets all the octopuses. But maybe I'll figure that out tomorrow. All right. Thanks as usual to all the sponsors of Advent of Code, including my current employer, Akita Software. Check out our jobs page. We'd love to have you come work for us. And I'll be back tomorrow night.